Alright, let's go. Number 10. The Wall of Fire at the edge of the solar system. On August 25, 2012, Voyager 1 crossed an invisible boundary that no human-made object had ever touched. NASA scientist Ed Stone announced the spacecraft had entered interstellar space, passing through a region called the heliopause, the outer edge of our sun's magnetic influence. What Voyager 1 recorded just before crossing this threshold disturbed the scientists studying its data for years afterward. The spacecraft measured temperatures approaching 50,000 degrees Celsius, a region of superheated plasma that researchers began calling the Wall of Fire. The science behind this boundary is rooted in basic stellar physics. Our sun produces a constant stream of charged particles called the solar wind, which inflates an enormous bubble of influence extending billions of kilometers in every direction. At the edge of this bubble, the solar wind collides with the interstellar medium, the thin soup of gas and particles that fills the space between stars. The collision creates a shock front where particles are heated to extreme temperatures, forming a shell of ionized gas that surrounds our entire solar system. But here's where the measurements become unsettling. The Wall of Fire isn't a uniform barrier. Voyager 1's instruments detected strange fluctuations, pockets of magnetic turbulence, and regions where the boundary appear to ripple in ways that current models cannot fully explain. The spacecraft is still transmitting data about this region, and each new measurement reveals phenomena that scientists didn't predict. Something about the interface between our solar system and the galaxy beyond operates according to rules we don't yet understand. The truly disturbing aspect is what this boundary means for Voyager 1's future observations. The spacecraft is now traveling through a medium shaped by forces we've only glimpsed. Every measurement it sends back represents data from an environment humanity has never directly sampled. And as Voyager 1 moves deeper into this unmapped territory, its instruments continue detecting anomalies that suggest our understanding of the space between stars is dangerously incomplete. We sent a machine to listen to the silence beyond our sun, and it keeps finding things that shouldn't be there. Number 9. The tsunami waves from dying stars. In 2014, astrophysicist Don Gurnett at the University of Iowa noticed something extraordinary in Voyager 1's plasma wave data. The spacecraft had detected a massive disturbance rippling through the interstellar medium, a pressure wave so powerful it took months to pass through the region of space surrounding the probe. Gurnett's team called these events tsunami waves, and they discovered that Voyager 1 had already recorded 3 of them since entering interstellar space. Each wave caused the plasma around the spacecraft to oscillate at measurable frequencies for extended periods. The origin of these waves traces back to events at the surface of our sun. When the sun produces a coronal mass ejection, a massive burst of plasma and magnetic field, the resulting shockwave travels outward through the entire solar system. These shockwaves eventually reach the heliopause, pass through it, and continue propagating into interstellar space. The waves compress the plasma surrounding Voyager 1, causing electrons to oscillate and producing the signals the spacecraft detected. We were essentially hearing the echo of our own sun's violence reaching into the galaxy beyond. What makes these tsunami waves particularly disturbing is what they reveal about the interconnectedness of cosmic phenomena. Voyager 1 is measuring pressure waves that originated hundreds of millions of kilometers away, demonstrating that events at our sun's surface propagate into the broader galaxy with measurable effects. But if our modest sun can send detectable waves across interstellar distances, what waves are being sent toward us from more violent events elsewhere? Supernovae, neutron star mergers, and black hole collisions all produce disturbances that ripple through the same medium Voyager 1 is now sampling. The spacecraft might eventually detect the echo of a dying star, a stellar explosion whose light reached Earth centuries ago, but whose pressure wave is still moving through the galaxy. Voyager 1 will measure disturbances from events it cannot see, from stars that died before humans evolved, from cosmic catastrophes whose full scale we cannot comprehend. Every tsunami wave it detects is a reminder that the space between stars is not empty. It is filled with the fading screams of dying suns, and our small probe is swimming through the acoustic graveyard of the galaxy. Number 8. The persistent hum of interstellar space. In May 2021, a team led by Cornell University doctoral student Stella Koch-Acker published a paper in Nature Astronomy describing something that shouldn't exist. Voyager 1's plasma wave instrument had detected a steady, faint signal emanating from the interstellar medium itself, a narrow band of radio emission at approximately 3 kHz that persisted continuously across years of observation. The researchers called it the hum of interstellar space, and they had no definitive explanation for what caused it. The hum is produced by something interacting with the plasma surrounding Voyager 1, but the source remains mysterious. Unlike the tsunami waves, which arrive as discrete events and then fade, this signal never stops. It doesn't correspond to any solar activity, any known stellar source, or any predicted natural process. The plasma of interstellar space is simply vibrating at a specific frequency for reasons that current physics cannot fully account for. Voyager 1 has been listening to this hum for years, and it shows no signs of weakening or changing. But here's where the implications become deeply strange. The hum tells us that the medium between stars is not quiet. It has a baseline signal, a constant frequency that exists everywhere Voyager 1 has measured. This means every region of interstellar space the probe will ever enter is already vibrating at this frequency, suggesting the hum is a fundamental property of the galaxy itself. Something is causing the entire interstellar medium to resonate, and we're just now learning it was doing so the entire time humans have been looking at the stars. The truly disturbing aspect is what future measurements might reveal about this signal. As Voyager 1 travels deeper into interstellar space, its instruments may detect variations in the hum that correspond to structures we cannot see, density waves from ancient supernovae, magnetic field lines stretching across light years, or phenomena that haven't yet been theorized. The hum is the voice of the galaxy speaking at a frequency we only learned to hear a few years ago, and it has been speaking for billions of years, broadcasting information about the structure of space that Voyager 1 will continue to decode until its power finally fails. Number 7. The magnetic highway no one predicted. In 2013, NASA announced that Voyager 1 had entered a region of space that scientists had never imagined could exist. The spacecraft's magnetometer was detecting something unprecedented, a zone where magnetic field lines from our sun appeared to connect directly with magnetic field lines from the galaxy beyond. Physicist Leonard Berlanga called it the magnetic highway, and its existence forced researchers to redraw their models of how our solar system interfaces with the rest of the galaxy. The magnetic highway operates according to principles that weren't predicted by any pre-Voyager theory. In this region, charged particles from our sun can flow outward into interstellar space, while high-energy cosmic rays from distant stellar explosions flow inward toward the sun. The magnetic field lines act as conduits, allowing the exchange of particles between our solar system and the galaxy at rates far higher than previous models suggested. Our solar system is not the sealed bubble scientists once imagined. It is connected to the broader galaxy through invisible pathways that Voyager 1 discovered by accident. What makes this discovery particularly disturbing is what it implies about the flow of material into our solar system. Cosmic rays are not harmless background radiation. They are subatomic particles accelerated to near light speed by the most violent events in the universe, supernovae, pulsars, and active galactic nuclei. These particles carry enough energy to damage DNA, disrupt electronics, and penetrate deep into planetary atmospheres. The magnetic highway allows more of these particles to reach our solar system than scientists previously calculated. Voyager 1 will continue mapping this network of magnetic connections as it travels outward, and each measurement may reveal new pathways that deliver cosmic radiation into our neighborhood. The spacecraft might detect evidence of particle streams from events that occurred thousands of light years away, still flowing through magnetic channels that reach down to Earth. We are not isolated from the violence of the galaxy. We are plugged into it through invisible cables, and Voyager 1 is the first probe to feel their pulse. Number 6. The density anomalies that shouldn't exist. In October 2020, Cornell University astronomers published findings that deepened the mystery of interstellar space. Analysis of Voyager 1's plasma density measurements revealed that the region beyond the heliopause is significantly denser than predicted by decades of theoretical work. The interstellar medium surrounding the spacecraft contains approximately 40 times more electrons per cubic centimeter than the outer regions of our solar system, a dramatic jump that occurs within a surprisingly narrow boundary zone. The density gradient Voyager 1 measured shouldn't exist according to standard models of galactic structure. Scientists had assumed the transition from solar system to interstellar space would be gradual, with plasma density increasing smoothly over large distances. Instead, the probe found sharp, unexpected jumps in density occurring over distances of just a few astronomical units. Something is concentrating interstellar plasma in ways that current physics doesn't predict, creating pockets of denser material embedded in the broader galactic medium. But here's where the measurements become troubling. Voyager 1 has already detected multiple density jumps since entering interstellar space, and each one required revision of existing models. The probe is essentially mapping a region that looks nothing like what theorists expected, and each new measurement adds to a growing catalog of anomalies. We thought we understood the space between stars. We were wrong in ways that Voyager 1 continues to document with every transmission it sends. The truly disturbing aspect is what future density measurements might reveal. If the interstellar medium contains unexpected structures at the scale Voyager 1 is currently sampling, the galaxy may be far more turbulent and varied than astronomers have modeled. Ahead of the spacecraft lie regions of potentially even higher density, in zones where the plasma becomes thick enough to affect starlight traveling through it, and possibly structures that interact with passing stellar systems in ways we haven't calculated. Voyager 1 will spend its final functioning years charting this hidden terrain, revealing that the emptiness between stars is neither empty nor uniform, but something far stranger. Number 5. The final transmissions from a dying probe. Voyager 1 is powered by 3 radioisotope thermoelectric generators, devices that convert the heat of decaying plutonium-238 into electricity. When the probe launched on September 5, 1977, these generators produced approximately 470 watts of power. As of 2024, that output has dropped to around 230 watts, and it continues to decline by approximately 4 watts per year. NASA engineers have been systematically shutting down instruments and heating systems to conserve power, a process they call the slow death of the spacecraft. The physics of Voyager 1's power decay are unforgiving. Plutonium-238 has a half-life of 87.7 years, meaning the fuel source is inexorably losing the ability to generate heat. By the early 2030s, the spacecraft will no longer produce enough power to operate any scientific instruments. The probe will still physically exist, still travel outward at approximately 61,000 kilometers per hour, but its ability to communicate with Earth will have permanently ended. Humanity's farthest emissary will become a silent object drifting through the galaxy. What makes this timeline particularly disturbing is what Voyager 1 will detect in its final years of operation. The probe's remaining instruments may measure phenomena that it cannot report, anomalies that flash across its sensors moments before the power fails entirely. There may be a final burst of data, a last transmission containing measurements of something unprecedented that arrives at Earth after the spacecraft itself has gone dark. We will receive the probe's dying words decades after they were spoken. Traveling at the speed of light across a gulf of space the machine itself can no longer bridge. The cruelest aspect of Voyager 1's death is what it will continue experiencing without the ability to tell us. The spacecraft will pass through regions of interstellar space no human instrument has sampled, encounter magnetic structures and density variations that would rewrite our understanding of the galaxy, and potentially detect phenomena we cannot yet conceive. All of it will occur in silence. The probe will witness the cosmos for millions of years after its voice fails, carrying its sensors through territory that will remain forever unmeasured. We launched a machine to explore the galaxy, and the galaxy will outlast its ability to describe what it sees. Number 4. The interstellar cloud that will swallow the probe. Within the next few thousand years, Voyager 1 will exit the local interstellar cloud, a diffuse region of gas and dust approximately 30 light-years across in which our entire solar system currently resides. Beyond this cloud lies a region called the G cloud, and beyond that, even denser structures that astronomers have only begun to map. Each transition involves the spacecraft moving into environments with different densities, different chemical compositions, and different magnetic properties than anything it has yet encountered. The local interstellar cloud formed approximately 150,000 years ago from material ejected by ancient stellar explosions, and our solar system entered it sometime within the last 60,000 years. Before we were inside this cloud, the environment surrounding our sun was significantly different, potentially offering different levels of cosmic ray exposure and different interactions between the solar wind and the interstellar medium. When Voyager 1 eventually exits the cloud, it will enter a boundary zone where the two environments meet, a transition region similar to the heliopause but on a far larger scale. But here's where the mission trajectory becomes unsettling. Voyager 1 will still be physically intact when it crosses these boundaries, continuing to travel at its current velocity for millions of years. The probe will pass through multiple interstellar clouds, through regions of varying density, through zones where the galactic magnetic field takes on different configurations. Each transition represents an environment that might have affected Earth's climate and biosphere in ways scientists are only beginning to understand, but the spacecraft will no longer be able to report what it experiences. The truly disturbing aspect is what the local cloud might hide. Some astronomers have proposed that passages through denser interstellar clouds could strip away the heliosphere, exposing Earth to significantly higher cosmic ray flux and potentially triggering ice ages or mass extinction events. Voyager 1 is currently sampling the edge of such a cloud, and its measurements will provide the only direct data humanity ever collects about what happens at these boundaries. The probe is teaching us how our planet's long-term habitability depends on our location within a galactic structure we only discovered because a machine we built kept sending back data that didn't match our expectations. Number 3, the approach to another star. In approximately 40,000 years, Voyager 1 will make its closest approach to another stellar system. The spacecraft's trajectory will carry it within 1.6 light-years of a star called Gliese 445, a red dwarf currently located in the constellation Camelopardalis. At that distance, the probe will be deeper inside another star's sphere of influence than it currently is inside our own solar system. It will be the first human-made object to effectively enter the gravitational neighborhood of another star, a passage that represents a form of interstellar contact humanity will never directly witness. Gliese 445 itself is unremarkable by stellar standards. It's a small, dim, red dwarf approximately 17.6 light-years from Earth, with no known planets and no particular significance to astronomers. But Voyager 1's encounter with this star is profoundly significant for another reason. The spacecraft carries the golden record, a 12-inch gold-plated copper disc containing sounds and images selected to portray the diversity of life and culture on Earth. If any civilization ever intercepts Voyager 1, the golden record is what they will find. What makes this encounter particularly disturbing is what it means about the timescale of human reach into the galaxy. Voyager 1 will take 40,000 years to approach a single nearby star, and even then, it will pass at a distance where the probability of detection by any hypothetical civilization is essentially zero. The spacecraft represents humanity's fastest, farthest, most ambitious attempt to project ourselves beyond our solar system, and it will drift silently past a star without ever getting close enough to matter. Our species will likely be extinct or unrecognizably transformed long before the probe completes this simple crossing of interstellar space. The truly unsettling aspect is what Voyager 1 will witness during this passage. The probe will experience Gliese 445 as a brightening point of light growing steadily stronger, then fading again as the spacecraft continues onward. This silent flyby will occur in complete darkness, with no instruments functional and no transmissions possible. The first star humanity ever approached with a physical object will receive a dead machine carrying a message from a civilization that no longer exists. Voyager 1 will keep its appointment with Gliese 445, whether anyone is left on Earth to remember why it was sent. Number 2, the Golden Record and what might find it. The Golden Record attached to Voyager 1 was curated by a committee led by astronomer Carl Sagan and launched with the spacecraft in 1977. It contains 115 images, greetings in 55 languages, a selection of music spanning human cultures, and sounds from Earth, including whales, thunder, and a human heartbeat. The record also includes a diagram indicating Earth's location using the positions of 14 pulsars as reference points. Any civilization that recovers the disk will possess a map leading directly to our planet. The design of the Golden Record is remarkable. It's engraved with instructions for playback using purely mathematical and physical principles, ensuring that any civilization with a basic understanding of science could extract its contents. The disk is electroplated with a sample of uranium-238, which has a half-life of 4.5 billion years, allowing future discoverers to calculate how long the record has been traveling. The record is designed to survive and to communicate across timescales that dwarf human history. But here's where the implications become troubling. The decision to include Earth's location on the record was controversial among scientists even at the time of launch. Physicist Freeman Dyson and others argued that broadcasting our position to unknown civilizations carried significant risk, given that we have no way to verify the intentions of any species that might find the disk. The counter-argument, championed by Sagan, was that Voyager 1 travels so slowly and passes so far from other stars that the probability of detection is vanishingly small. Both sides may have been right about the statistics and wrong about what actually matters. The truly disturbing aspect is what happens if the Golden Record is ever recovered. Voyager 1 will travel through the galaxy for billions of years, potentially outlasting our sun and our species. Across that time scale, the probability of the disk being detected by some civilization, some automated system, or some phenomenon capable of decoding it is no longer zero. The record will eventually be found. Whoever finds it will know where we were, what we sounded like, what we looked like, and roughly when we existed. Voyager 1 is a message in a bottle thrown into an ocean we have never mapped, and the shore where it eventually washes up is one we cannot see from here. Number 1, the silent eternity. Voyager 1 will continue traveling through the galaxy long after Earth is gone. Current projections suggest the spacecraft will remain physically intact for billions of years, drifting through interstellar space at approximately 61,000 kilometers per hour. It will outlast the Sun, which will exhaust its hydrogen fuel in roughly 5 billion years and expand into a red giant that destroys the inner solar system. It will outlast Earth, which will be rendered uninhabitable long before the Sun's death. Voyager 1 will still be traveling when every trace of human civilization has been erased from our home planet. The probe's trajectory will carry it on a slow, nearly eternal journey around the galactic center. Voyager 1 is traveling at approximately 17 kilometers per second relative to the Sun, which is fast by human standards but extraordinarily slow compared to galactic distances. At this velocity, the spacecraft will take approximately 225 million years to complete a single orbit around the Milky Way. During that time, it will pass through regions of space currently unknown to astronomy, witness stellar formations and deaths across billions of years, and drift through environments that will continue changing long after its instruments have failed. What makes this eternal journey particularly disturbing is what it represents about the permanence of our actions. Voyager 1 is a physical record of humanity that will persist on timescales comparable to the evolution of life itself. The probe will still exist when continents have rearranged, when new species have evolved and gone extinct across multiple cycles, when the constellations we know have drifted into unrecognizable patterns. Everything about the civilization that built it will have changed or vanished, but the spacecraft will continue onward, unchanged except for the slow erosion of cosmic dust and radiation. The truly horrifying aspect is the silence of this journey. Voyager 1 will travel for billions of years without any possibility of contact, without any way to record what it witnesses, without any observer to know what it has become. The probe will pass through regions of the galaxy that have never been mapped, encounter phenomena that no theory has predicted, and continue its endless drift through a universe that may one day contain no one who remembers sending it. We launched a machine to explore the cosmos and gave it a task it will complete long after we are gone. Voyager 1 is humanity's longest-lasting creation, and it will spend eternity carrying our memory through a silence we cannot imagine, toward destinations we will never know. If you want to see more videos like this, click the video on screen now and make sure to subscribe.